Okay, so here is the AP Classroom for Chapter 6. I thought I'd try it on here and send it to you and put it out there. So let's look at it. Chapter 7, I apologize. So the height requirement for certain ride and amusement park is 48 inches or taller. Distribution of height of 6-year-old children is approximately normal, need that, with a mean of 45.2 and standard deviation of 1.75 inches. Which of the following is the closest to the probability that a randomly selected 6-year-old will not meet? So that would mean be less than 48 inches tall. Height requirement for the ride. Notice there's nothing about a sample size here, so we are of course going to use norm CDF. We have a lower bound, 0 is fine. Obviously 0 is weight. There's nobody that's 0 inches tall. Our upper bound should be 48. We want to know what's the probability of not being able to ride the ride. With it being a normal CDF, we don't need to worry about being exactly on 48. Yes, somebody 48 inches tall could ride the ride, but we're talking one height out of infinitely many, so the probability of being there is basically 0, even though we know somebody could be, but we don't need it. It won't change our calculations. So our mean is 45.2, and our standard deviation is 1.75. If this had some sample size, then we'd have to do something with this 1.75, but this is just a good old-fashioned one. And I believe if we do this, we should get 94.9452. Okay. Continuous variable n has a normal distribution. We need normal. With a mean of 7.5 and a standard deviation of 2.5, which the following is probably equal to 0. And so this is that thing of a normal distribution has infinitely many, wouldn't let me draw, infinitely many, and here's 7 point, that was terrible drawing. So we could have literally any number around that. So we can be less than 8. If 8 is over here, that would be all of this. We can be, if this is 8, that'd be everything over here. Greater than 8 would be that. In between 7 and 8, we could calculate that area, and we could be less than 7 or above 8, but we can't be equal to 8. There's infinitely many numbers in there, and so the probability being exactly at one of them is basically 0, like we've talked about before. Okay. Data will be collected for the following variables. Which variables must likely be probably by a normal. The distribution of number of books read last week by the middle school students, where the right tail is longer than the left. That's definition of skewed right. Distribution lifespan of minutes for batteries of a certain size, where most lifespans cluster around the center, with some very low and some very high. That's probably our answer. That is our answer. Just seeing why the other ones are wrong. Distribution of ages and years of current students, where most students are between 18 and 22, but the ages greater than 22 are more spread out than ages less than 18. Again, that's definition of skew. Distribution of the number of birthdays per month for the employees at a certain company, where the number of birthdays in each month is approximately equal. That's a uniform. Everything's got the same probability. Distribution of length and stay in days of hospital after surgery, where many patients have very short hospital stays, but some stays are quite lengthy and considered high outliers. Well, again, that's your definition of skew. So only the battery life question there is what we're looking at. All right. So question 4. Distribution of time needed to complete a certain program test is approximately normal, with mean 47 minutes. So we're talking about means and not proportions. It's an deviation of 6 minutes. Which is the following is closest to the probability that a randomly chosen task will take less than 34 minutes or more than 60 minutes? So we actually have to calculate 2, and this comes into play quite a bit. If you think about it, this is just a good old one. We don't have a sample size again. So this is 47. So we want less than 34. So we want that, or more than 60, and or means add. So we want that. So we'd have to do 2 normal CDFs. Well, there's a way to do it with one of So our lower bound would be 0, our upper bound would be 34, and 47, and 6. And then we'd add to that norm CDF. Now we'd go, this was what, 60 minutes? So 0, 60, up to, I don't know, some high number, 47, and 6. Add those together. We should get 0.0303. The other thing you could do is 1 minus all of this area. So you could do 1 minus norm CDF. Lower bound 34, upper bound 60, 47, and 6. Now again, this one has no sample size. Don't need to worry about figuring out new standard deviation, anything like that. So let's move on to the next one. International Polling Agency estimates that 36% from country X were married between the age of 18 and 32, 26% from country Y. Based on the estimates, which of the following close probably the difference proportion from random sample of 60 adults from country X and a random sample of 50 adults from country Y were first married before one is greater than 0.15. So we want X minus Y to be greater than 0.15. So this is going to be our lower bound, and then up to 1, upper bound will be 1. Because we are talking proportions. Let's see, probability, it's usually 36%. When we see percentages, we think of adults. So we need mu of X bar minus Y bar equals mu of X minus mu of Y. So mu of X, oh, this is not this, I'm sorry. I apologize. P hat X minus P hat Y. And so that's just going to be PX minus PY. Because these are proportions, I'm sorry. So that's going to be 0.36 minus 0.26. So there is 0.10. That's our mean. Our standard deviation, we're going to use it, so it's P hat X minus P hat Y will be a very long, so it's PX1 minus PX over NX plus, always plus, PY1 minus PY over, I don't want, I put N in right there, right? NY. Our sample size, NX is 60 and NY is 50. The 18s and 32s mean nothing here. So PX is 0.36, 1 minus 0.36 over NX was 60 plus, was it 0.26? 1 minus 0.26. It's a lot of work for multiple choice problem. So let's throw all this into the calculator. See if I can bring up my calculator here on your screen and see what happens. All right. So we're going to do this somewhere. Okay, I'll move that over there. Control square root and then control divide. And so that was 0.36 times 1 minus 0.36. Over 60, that's correct, plus control divide again, 0.26, 1 minus 0.26 over 50. So there should be our standard deviation. So now we can do menu, probability, statistics, whatever you want to do, distributions. Either way, you'll get there. Norm CDF. So our lower bound should be 0.15. We want the difference to be greater than 0.15. Our upper bound would be 1. Our mean was 0.10, and our standard deviation, naturally, I didn't write down. And I can't move that, I don't think. Oh, I can. I think you can do that, but 0.087, 0.87476. Let's hope that comes out to a number that's an answer choice for us. Where'd it go? Why did that not actually do anything? That's lovely. All right, let's try that again. Menu. Now let's go probability this time. Doesn't matter. It's under distributions. Norm CDF. Lower bound is 0.15. Upper bound is 1. And we are talking about 0.10 and 0.08746, I think. And that's still producing nothing. Why is this giving? All right, give me a second here. Sheesh, finally. Okay, so we get about 0.08238 on here, which is close enough to one of our answer choices. Right there, 0.028. Good enough. Sorry for all that confusion. Calculators are fun. Okay. Recent survey, the proportion of adults who indicated mystery as their favorite type book was 0.325. Hey, look, proportions. You're always wondering which one we're doing. Two simulations we conducted for the sampling distribution of a sample proportion for a population with a true proportion of 0.325. Sampling A will consist of 1,500 trials with a sample size of 100. Simulation B will consist of 2,000 trials with a sample size of 50. Which of the following describes the center and variability for A and B? Okay, number of trials shouldn't matter. As long as they're both pretty high, well, it really shouldn't matter. We're going to get the same center. The same center is going to be 0.325. The center of any sampling distribution, it doesn't really matter the sample size. The center will be the center. The center is just whatever the original one was. So both of these will have a center of 0.325. But a sample of size 100 versus sample of size 50, the 100 is going to have smaller variability than the sample of size 50, because we do one of them be 0.325 times 1 minus 0.325 over 100, and that's going to be less than 0.325 times 1 minus 0.325. Why can't I get my, maybe it's because of this. Thank you, over 50. So centers will be roughly equal. So we can get rid of greater than, less than for centers. And A will not be greater, the variabilities will not be equal. So simulation, the variability of simulation and standard deviation will be less than 1 per minute. The higher the sample size, the lower the variability. Okay. Number 7. We see in attendance records at a large high school show that 6% of students are late to school on a typical day. The 6% proportions again. The students in the AP statistics class believe that the rate is higher than 6%. The students took a simple random sample of 75 students from the school and asked, were you late to school today? In their sample, 6 out of the 75 students, or 8% of the sample, said they were late for school that day. AP statistics students conducted a simulation of 100 samples of 75 students where a population where 6% of the students were late. The results of the simulation were so. So they assumed what they had been told, that 6% was the true proportion. but they got 8% when they did it, so they want to see what the probability of 8%. So here is the true proportion, P. Well, they got 8% or more, which they're saying now, based on the simulation and the results of the AP class sample, what is there convincing statistical evidence that more than 6% of students? So this is probably going to come out. I'm seeing 29% a lot. So there's 1, 2, 3, 4, 5, 6, 7. Oh, I could count here. I'm sorry. So that looks like about 17. And here's 10. Here's 2. So there's 29%. So it's 29 out of 100 samples. Each one of those is a sample. So 29% of the time, if 6% is true, on any given day, 8% or more would be late 29% of the time, just by random sampling. So no, because about 29% of the simulated samples, simulated sample percentages of students late school, 8% or more. That'd have to be a much more. This is where this needs to be less than 5% for this to have convincing statistical evidence. So no. Okay. Survey recently indicated the mean time spent on a music streaming service about 210 minutes per week for the population of a certain country. A simulation was conducted to create a sampling distribution with a mean of 210. So we're talking about an average here, a mean of 210. And we even see mean of 210. So not proportions, means. Kind of doesn't matter in this case. The following histogram shows the results of the simulation. Which of the following would be the best reason why a simulation is not approximately normal? In order for it to be normal, we either have to have an original distribution that's normal, which we're not told anything about that. For means, then we need a big enough sample size, at least 30. So what this tells us has nothing to do with being random, but the sample size was not sufficiently large. We'd need at least 30. So this is our guy right here. The population distribution was approximately normal. No, if the original population distribution was normal, then this would be normal. The samples were selected without replacement. That has nothing to do with this. The sample means were less than the population. That, again, that has nothing to do with it. So when you see skewed data from a sampling distribution, it means your sample size was not enough. Okay. Census of an entire population was conducted, and you get this graph. Weird looking graph. Looks like the Sauron's tower from Lord of the Rings. Sampling distribution where it samples of size 2. So the idea here is if I'm only taking 2 at a time, there's a fairly decent chance I either get 1 from here and 1 from here, which would average out into the middle, or I get 2 from over here or 2 from over here. So we'd have kind of, a lot of them here, and we kind of have, 2 over here and a lot of 2s over here. So we're going to end up getting that guy right there. Most of it's going to average out into the middle, but you are going to get clumps of sets of 2s that come from here and clumps of sets of 2s that average out really high, and that's what we get. Here's those sets of 2 that come from the high part, sets of 2 that come from the low part, and these are the sets of 2, 1 coming from each side. And the rare chance we'd get something 2 in the middle, but they would average out to the middle as well. Okay. A recent report indicated 90% of adults in a certain region actively try to include vegetables in their diet. A simulation was conducted that consisted of 50 trials with a population parameter of 0.9. Each trial consisted of sample size 10. 90%, so we're talking about proportions. 50 trials, number of successes out of 10 recorded with where success represents adult in trying to include vegetable in their diet. 5 published simulations are shown. Which one is best to match? So the population parameter is 90%. And we're talking samples of size 10. So basically, we should get something at 90%. These are out. These are counts. They don't say 90%. This is out because we should have a bunch of stuff clustered around here. Well, this one's out because it also says 9 and blah, 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 not 90%. So the only one's left is this because these are percentages. Okay, so we're talking about proportions, so we can lose our counts. All those go away. This one goes away because it's not centered, or it's not, its average would not be the population average. All right. A certain statistic, d hat, is being used to estimate a population parameter d. The expected value of d hat is not equal to d. What property does d hat exhibit? That's the definition of biased. If the expected value of d hat is not equal to the population parameter, then it's biased. That's, again, bias for us, we're talking about, it's just bad sampling or something like that. It's not personal bias or anything like that. It's non-response, it's undercoverage, it's response bias, something like that. Which of the following conditions will create a biased estimator in a population parameter? Well, we just said it. The expected value of the estimator is not equal to the population parameter. That's definition of statistical bias. More on bias here. It says following graphs show the sampling distribution for two different point estimators R and W of the same population parameter. Which of the following is true? Okay. Basically, this one is biased. If this is the true thing, but it's true is this guy, that means this is biased. This one is centered around that, so this is unbiased. Now, for the record, the actual shape doesn't matter. This is a good estimator, but for bias, a good estimator has low variability and low bias. But low bias can come from any kind of thing. Like if there were even, if it was much more spread out, as long as it was centered on the parameter, it's fine. Okay, so R is biased and, R is biased and W is unbiased. All right, moving right along. Certain statistic will be used as an unbiased estimator parameter. Let J represent the sampling distribution of the estimator size 40, and K represent the distribution for samples of size 100. So if they're unbiased estimators, which it tells us, that means the expected value of them will be equal. So that means we can get rid of this. We can get rid of this. We can get rid of, we can get rid of those two. So the size 40 and 100, K is going to have the standard deviations of J will be, J's SD will be greater than K's SD. So they won't be equal. The variability of it will not be equal. It looks like, am I seeing equal? Weird, it looks like A and D are kind of the same answer. Anyway, it doesn't matter because they're both wrong. Variability of J will be greater than the variability of K. All right. Question 15. X bar is used as an estimator for mu. Plain and simple. Researchers will conduct a study of television viewing habits of children. They will select a simple random sample of children and record the number of hours of television the children watch per week. Researchers will report the sample mean as a point estimate for the population mean. Which of the following statements is correct for the sample mean as a point estimator? A sample of size 25 will produce more variability of the estimator than a sample of size, So as the sample size goes up, variability goes down. So 25 will have more. So it's not that sample size. They won't be biased if it's a true random sample. They won't. So we have nothing about bias. So there you go. Sample size 50 will have less variability than a sample size 25. Bag contains chip where 27.5% are blue, percent, so that's, we're talking proportions. Random sample of 5 chips will be selected at a time and with replacement. So we can, that means we don't have to have the 10% condition, all that kind of fun stuff. What is the mean of standard deviation of the sample of size 5? Well, the mean is going to be of p hat is just p, which in this case is just 0.275. Standard deviation of p hat will be the square root of p times 1 minus p over n. So that's going to be square root 0.275, 1 minus 0.275 over our sample size 5. So that guy right there. Yeah, this one's bad because they're actually using the whole number of percentages. The rest of them don't even have anything divided by, so those are a no-go. Those are just if they were random variables, right? Expected values. If they weren't sampled. Manufacturer of cell phone screens has found that 5% of all screens produced have defects. Percent, so we're talking proportions. Let PD represent the population for cell phones that have screen defect, therefore PD is 0.05. For the sampling distribution of the sample proportions of cell phones screens from this manufacturer with a screen defect for sample of size 40 is mu of PD hat E is 0.05, which is the best interpretation. That's basically for all samples of size 400. Every possible group of 400, the mean of all those sample proportions will be 0.05. The mean of the means is the means. So take all the dots that could be done from sample size 400 and average them together, and you'll get 0.05. According to data from the United States Elections Project, only 36% of eligible voters voted in the 2014 elections. For a random sample of size 40, what is the best, which following best describes the sampling distribution of p hat, the sample proportion of people who voted in 2014. So if it's sample of size 40 and we have 36%, we need to be normal, we need n times p to be greater than or equal to 10 and n times 1 minus p to be greater than or equal to 10. So we need 40 times 0.36, which is 40 times 0.36, that's 14.4, which is greater than or equal to 10, of course, and 40 times 1 minus 0.36 is obviously going to be greater than or equal to 10 because it's a larger number. 40 times 0.64, is that right? 25.6 is greater than or equal to 10. So we are normal. So we get rid of our skews. We can do these. The mean is going to be 0.36, so we can lose that one. And our standard deviation our standard deviation should be P, so 0.36 times 1 minus 0.36 over our sample of size 40, and that should come out to 0.076, I believe. That's a 40, not a 90. There you go. Okay. Based on records kept at a gas station, the distribution of gallons of gas purchased by customers is skewed right with a mean 10 gallons and standard deviation of 4 gallons. So we're talking about means. So we're talking about means and not proportions. Random sample of 64 customers. There's our standard deviation. Random sample of 64 customers selected the sample mean of number of gallons recorded. Suppose a process selecting a random sample of 64 receipts and recording the sample mean was repeated for 100 samples, which is the following best dot plot created. So 64 for means, we need a sample, and we have that, so we can say it's normal. our sampling distribution. So it's not skewed right, it's not skewed right, it's not skewed right. The mean is going to be 10 gallons. So we got both of that there. And standard deviation is not going to be 4. It's going to be 4 divided by the square root of 64, which you can actually do that one. 4 over 8.5, right? Did I do my math right? God forbid. Naturally, the website's not moving. Give me a second. Yep, okay. So it's our 0.5. Okay, getting closer, 21. Consider a population of 4 children, 2, 5, 6, and 11. Population mean is 6 years, and the population variance, this one I was working on with a student earlier, variance of 10.5 square years. What the heck is a square year? Don't worry about that. So our variance is 10.5, and a variance is the standard deviation squared. It's before you square root it. So if random samples of size 2 are taken with replacement, the mean and standard deviation of the sampling distribution of all samples of size 2 is we're still going to have a mean of 6 years. And our standard deviation is going to be, 10.5 would equal the standard deviation squared. So the standard deviation is actually the square root of 10.5. And for that, so now we need that divided by our sampling distribution. It's the original standard deviation over the square root of the sample size. So the square root of 10.5 over the square root of 2. And offhand, I don't know what that is. And my website won't move. So God forbid, I'm going to have to use a calculator. So let's bring the calculator back up. AP Classroom is being buggy. I was trying to use, God forbid, use the enter key to there instead of having to actually do the math. And why won't this move? Okay. So control divide, control square root 10.5 over square root 2. And we get 2.29129. Is that one of our answer choices? Yep, there you go. Okay. Which of the following is a sampling distribution, the sample size X bar, sample for size 40? The mean is 85. So sample size 40, we're talking about X bar. So if n is greater than or equal to 30, we're normal. So our skewed ones can go away. But we need to have a mean of 85. So pretty close. We're good there. We're good there. Well, 85 would be way up here, so this one's out. The sample of size 40 is going to give us a pretty good, pretty small variance. So we should get that. All right? Okay. The graph below displays relative frequency for distribution X, the total number of dogs and cats owned per household for the households in a large suburban area. For instance, 14% of the households own 2 of these pets. According to local law, each household in this area is prohibited from owning more than 3 of these pets. If a household in this area is selected at random, what's the probability that a selected household will be in violation of this law? Show your work. So A, more than 3 means these people, or these people, or these people, or these people. So the probability that X is greater than 3 equals 0.07 plus 0.04 plus 0.04 plus 0.02, which should be what? 0.09 plus 0.08. Is my math right at 0.017? As AP Classroom still doesn't want to work, we'll go on from there. So, part B. If 10 households are selected at random, what's probably that exactly 2 of them will be in violation of this? We'll all show your work. 1 second. Let me see if I can get AP Classroom working. And yes, I just realized I skipped 23. I will go back and do that. So here we actually have a binomial. Just going back a bit here. We're talking about 3 pets or not. So binary. Either, sorry, not 3 pets. Either more than 3 or not. Independent. Yeah, we have got 10 households. 10 is less than 10% of households. Number of trials is 10. And the same probability each time. And violation. So we found our thing to be, here's our probability. Same probability. It's always going to be 0.17. So we can do binomial CDF, or PDF in this case. It says it's exactly 2. So we can use our calculator and do menu, probability, distributions, binomial PDF, not CDF. Menu, probability again, sorry, distributions, binomial PDF. Number of trials is 10. Probability of success is 0.17. And the X value we're looking at exactly 2. 0.2929. And so that's what we'd put. Binom PDF. And it was 10, 0.17. Oops. 2, and this is from the problem, and so that was 0.2929. There you go. Okay, C. The mean and standard deviation are 1.65 and 1.851. Suppose 150 households are selected at random. The mean number of dogs and cats per household is to be computed. Describe the sampling distribution, including shape, center, and spread. So we're going to do SOCVA. Shape. So we are talking about the mean number of dogs and cats per household. So we are going to use central limit theorem. N is greater than or equal to 30 because we're actually using 150. So the shape is normal. And we're not going to, it doesn't ask us to deal with outliers, just shape, center, and spread. Normally, generally, you wouldn't have outliers anyway. The center, so mu of x bar would just be mu, which is 1.65. And the spread, variability, whatever you want to call it, standard deviation of x bar is going to be the original standard deviation divided by the square root of the sample size. So we are talking 1.851 divided by the square root of 150. And so that's going to be 0.1511. And I'm just literally looking at the enter key there. But throw that in your calculator, and that's what you get. Okay, there's 24. Let me go back to 23 real quick, because I skipped that one. Okay. Students enrolled in honors biology at a high school were given a task of using a spreadsheet to program to investigate topic in genetics. All students in the class had a similar background knowledge of the topic. Some students, they all the same probability basically. Some students in the class had no spreadsheet experience, group R, and needed time to learn the program to complete the task. The rest of the students, group S, had previous spreadsheet experience and typically took less time to complete the task. Each of the histograms below show the distribution of completion time minutes for the two groups. Of the two histogram 1 and 2, which is more likely distributes completion time as a group? And student R justifies your result, justify your answer. Group R had to learn. Group S, this is the completion time. So most of them completed it first. So this is probably S. Most of them took longer to complete it. This is group R. So histogram, oh, I don't know why. You can do that. Okay. Histogram 2 is most likely group R. They, on average, took more time to complete the task. Simple as that. Okay, part B. Describe the shape of the histogram of the two groups of students combined. When we're combining two skewed groups, we're not told anything about sample sizes or anything like that yet. You end up with a bimodal. So the shape would be bimodal, not bimodal. One skewed right, one left combines to a bimodal. Outliers, we don't really have any outliers. The center center would be basically the center of both of them. Probably would this you're going to average out to about 75. Center, it would average to roughly 75. And the spread, we wouldn't know anything about any kind of standard deviation or anything like that. We can just talk about the, we'd go from 115 minus 35. So our spread is about 80, our range. Consider the population of all students in the honors biology class in the high school state who are given the task of using a spreadsheet to investigate the topic. The distribution of completion times is a shape similar to the combined histogram of students in high school. The mean 70 minutes and standard deviation 26.5. For a random sample of 50 students taken from that, describe the sampling distribution and sample mean completion time. So our shape by the central limit theorem is if n is greater than, so n equals, in this case, 50, which is greater than or equal to 30. So the combined thing will be a normal distribution. Our center, we wouldn't have to worry about outliers, is going to be mu of x bar equals mu, which equals 26.5 minutes. And our variability, we're not given anything, I think, here about standard. We're given a standard deviation. Oh, I'm sorry. I just misread that. 26.5 is standard deviation. So this should be 70. So our variance, our standard deviation of x bar would be the standard deviation over the square root of the sample size. So that's going to be the 26.5 divided by the square root of, what was our sample size? 50. And just magically I can do that in my head and see that should come out to 3.75 minutes. All right. Let's move on to 25. Okay. A lot of reading. In the western United States, water is sometimes diverted from mountain streams and rivers to be used for agriculture and municipal water supplies. Diverting too much water raises the water temperature in the mountain streams and rivers, affecting the fish that live there. Certain mountain rivers, an abundant brown trout has water diverted from its for city use. Assume the water temperature along all locations of the river has distribution with a mean of 18 degrees Celsius, standard deviation of 2 degrees Celsius. So we're talking means again, so not proportions. And there's our standard deviation. So mu. Okay, so mu is 18 degrees Celsius and standard deviation is 2 degrees Celsius. Sport fishing group plans to measure the water temperature at 64 randomly selected locations along the river. Worth noting, 64 is less than 10% of all locations. It would be almost infinitely many. Let the random variable F represent the water temperature 64. So N is going to equal 64. Large metropolitan diverted water is also planning to measure the same water to 100 randomly. So this is called this N1 or N, I guess, F. And so this will be ND. And so because of sampling variability, the sample collected by the water district is likely to yield a sample mean with water temperature different from the sample temperature. Let the random variable D represent the mean water temperature in degrees Celsius of 100 locations along the river selected. Describe the distribution of D minus F. We'll start here. Describe the distribution of F. Okay? So because N is 64, the shape N is equal to 64, which is greater than or equal to 30. So normal by the central limit theorem. The center should be 18 degrees. U of F, 18 degrees, degrees Celsius, and standard deviation would be of F, would be the standard deviation over square root of 64. So we're talking 2 over square root 64, which should equal 0.25 degrees. So brown trout, excuse me a second. Brown trout becomes stressed with over 18.3. Determine the probability F will exceed 18.3. So we can do, we just said it was normal, so we can do norm CDF, and our lower or bound, lower would be 18.3, upper something ridiculous, 100, that would be the water is boiling. I shouldn't put a comma there. And then mean is 18, standard deviation 0.25, and so that probability should be, do I have it right here? 0.11. Actually, let's just do it in the calculator real quick. So I've got 18, okay. So we'll do menu, see if this one works this time. Distributions, normal CDF. Lower bound 18.3, right? Upper bound 100, mean 18, and 0.25. So 11.11507. So we can call, 11, that's 507. So this is the part I was supposed to do that. Describe D minus F. So we're doing 100. So by CLT, 64 is greater than or equal to 30, and 100 is greater than or equal to 30. So both D and F and are normal. I run out of room. Therefore, I can't spell, D minus F is normal. So the center strangely, both of them are going to use 18 and 2 because they should both be the same temperature. It just depends on where they are. So it'd be, weirdly, 18 minus 18. So mu of D minus F is just 0. And the standard deviation would be square root, oh my gosh, let me just do it over here, I'm sorry. Standard deviation would be square root of 2 squared over 64 plus 2 squared over 100, which would equal around 32 degrees Celsius. And they didn't ask you to compute anything else, they just asked you that. So we get it again, normal by CLT 64 and 100 greater than or equal to 30. Mean is 18 minus 18, 0 degrees Celsius. And standard deviation we get up there is 32 degrees Celsius. There you go. There is all of Chapter 7.